So in this section, we're going to be talking about surfaces of revolution. So the idea, as illustrated in this diagram, is given some curve like this. In chapter 6, we talked about finding the volume by breaking this up into little disks and then adding up the volume of all those disks to find the volume of that region. Well, now we want to ask a related question. Well, what if instead of wanting to know the volume of said region, what if we want to know its surface area, right? So imagine now, instead of it being a solid volume, what if we wanted to know the material that would be needed, or the area of the surface of this? So the idea is based on the same thing that we've been doing. So imagine now we have some little region, delta x, and we take a little rectangle or a finite strip, and we want to find the surface area of the little piece that's right here, right? Well, in the last section, we came up with the following. So zooming in on that, if we had a little strip that looked like this, we had our delta x and our delta y, told us that the length of the hypotenuse was delta x squared plus delta y squared, right? That was the arc length formula that we did in 8.1. So we can figure out what the length of one of those pieces is. So now imagine if we were to rotate that little strip, or that length around the axis, what would be the surface area? So the idea is we're going to use the same idea that we did for volumes. We're going to subdivide this, but now imagine we have this little arc length that we're rotating around, and it makes a little dx or delta x thick surface as we rotate it around. So then to find the surface area, what do you think we would do? Well, what is the surface area of a similar 2D thing? So if we were going to cut this up into a piece, let's visualize what our strip looks like. So we would have a strip that looks like this, right? And we have our little arc length here. So what is the shape that we're making? Well, once again, it's a disk, but this time we have this circular thing that has a teeny bit of width to it that we're naming delta x. So what is the area for the surface, or what is the formula for the circumference of a circle? So what would one of those things be? So if we have this circle that goes all the way around, right, what would be the circumference of this circle? So what's the 2 pi r. So the circumference formula for a circle is 2 pi times r, right? Well, what would be the radius of that circle? Well, the radius, as it was in chapter 6, is going to be the distance, the perpendicular distance from the x-axis to the curve. So that's going to be our y-coordinate, or f of x, right? Either way you want to visualize it. So the radius, r, is going to be y. And then we have this little circle, but then how long is that little piece? Well, we made it teeny tiny thickness, so each little surface area chunk is going to be, so each little delta piece is going to be 2 pi r, so 2 pi y, times the length of this little piece. But last time we had it as delta x squared plus delta y squared. We defined this as delta s, or the change in arc length, right? So this little piece, or its length, is going to be that same delta s. So times delta s. And then if we were to add up all of those pieces, we would get that the surface area would be the integral from a to b of 2 pi times y times ds. Well, what was ds? Well, we go back to our previous section when we solved for this whole thing. Well, ds is what we came up with right here. So this piece, or more specifically this piece, which we wrote when we were calculating the arc length, is our ds. So we get our surface area is equal to this when we're rotating about the x-axis. How would our formula change if we were rotating about the y-axis? Well, we'd have the same thing, but everything would just be rotated, right? So instead of being the perpendicular distance from the x-axis to y, it would be the perpendicular distance from y to the curve out here. So what coordinate would that be? X, right? So we get an equivalent definition, which is the integral from some other values, c and d, of 2 pi x ds, and this is about the y-axis. So our ds can be factored in multiple different ways. So as we saw up here, we have delta x squared plus delta y squared. If we factor out a delta x, we get the formula that we got last time. So ds is 1 plus dy dx squared dx. Or if you factor out the delta y squared, you get ds is the square root of 1 plus dx dy squared dy. And we use the appropriate one depending on which our variable of integration is going to be. So since this one, we would be substituting out our x with x as a function of y, we would use this, and this would go with the first integral up here. And we'll clarify that with some examples. But either one of these gives us an equivalent definition for each. So I wrote all that out by hand, but it's also summarized right here on your handout, right? Okay, so let's go ahead and take a look at example number 1. So we wish to show that the surface area of a sphere of radius r is 4 pi r squared. Okay, so how are we going to do that? So we want to do something like this where we need a surface, so a surface of revolution. So what type of geometric figure would we need to rotate in order to get a sphere? A circle. Specifically, not the whole circle, just half of a circle, right? So if you have half a circle and you do a rotation, it will make a sphere. So we have options. So option 1 is we take our sphere, and it looks like this. or our circle of radius r that looks like this, where we have these 3 points. And the equation for that would be y equals the square root of r squared minus x squared, right? That's the equation of the upper half of a circle. There is another option that we have as well. And if we use a couple of the same points, so we have 0r, but then we also have 0, negative r, and the point r comma 0. Well, what if we have something that looks like this? If we rotate this about y, that would create a sphere. And if we rotate this about x, it would create a sphere, right? So the equation in blue up here would be x is equal to the square root of r squared minus y squared. And this all comes from the fact the equation of the circle is x squared plus y squared equals r squared. If I solve this equation for x by minusing y squared to the other side and taking the square root, that gives me this equation. If I solve for y by minusing x squared to the other side and taking the square root, I get this equation. Pardon me. All right. So now we want to use one of these two formulas. All right. So just because I feel like it, let's go ahead and use the rotation about the y. So that means we're going to use this one right here, and we're going to rotate about the y. So our limits of integration are going to be from negative r to r of 2 pi x times ds, right? Well, x is going to be what our function is right here. And ds, since we're substituting out our x as a function of y, we are going to select this ds to go with it. So then we are going to get this is equal to the integral from negative r to r of 2 pi times the square root of r squared minus y squared times our ds, where our ds is 1 plus dx dy squared and all of that in the square root dy. So we need to calculate dx dy. Well, that's just the derivative of this. So dx dy is going to be x is equal to the square root of r squared minus x squared, or x minus y squared, sorry. Our inner function is we have x of u is equal to the square root of u, which is u to the 1/2, and our inner function u is r squared minus y squared. So then our derivative, dx dy, by the chain rule, is dx du times du dy. So that gives us 1/2 u to the negative 1/2 times du dy is going to be negative 2y. Our 2's reduce out, and that gives us negative y over the square root of u. Substituting our u out, we get negative y over the square root of r squared minus y squared. All right, so we put all of that into our formula now, and we end up with the following. So the integral from negative r to r of 2 pi, so I'm going to pull the 2 pi out of our integral, square root of r squared minus y squared times the square root of 1 plus this thing squared. So negative y times negative y is positive y squared over the square root of r minus y squared squared is going to be r squared minus y squared dy. Getting our common denominator, we get r squared minus y squared plus y squared all over r squared minus y squared dy. The y squareds add to 0, and we get 2y times the integral from negative r to r of r squared minus y squared and our square root. In the numerator, the square root of r squared is going to give us r over the square root of r squared minus y squared. We're like, oh, well, that's a miracle. Then these two things reduce out, leaving us with 2 pi times the integral from negative r to r of r dy, but r is a constant. So we get our antiderivative is 2 pi r y, evaluated from negative r to r. So that gives us 2 pi r times r minus a minus r. So we get 2 pi r, and r minus a minus r is 2r. So that gives us 4 pi r squared, which we know from geometry is the surface area of a sphere, right? So we verified the geometric formula that we use, that the surface area of a sphere of radius r is going to be 4 pi r squared. So in this example, I chose to do the integral with respect to y and rotate this way. If you do it the other way, it's actually the exact same problem because of symmetry. The only difference is instead of y's, you'll have x's, right? But it will work out to be similar. So we need to select the appropriate surface area formula depending on which axis we are rotating about. We also need to pick the appropriate ds to match which variable we are integrating against. All right. So let's take a look at example number 2. The arc of the curve y equals cosine x from 0 to pi over 2 is rotated about the x-axis. Find the surface area. Okay. So we're rotating about the x-axis, and we have the curve y equals cosine x from 0 to pi over 2. So I'm going to draw a sketch to help me out. Here's my x, here's my y. I'm going to put 1 here, and then pi over 2 is like 1.5, so we'll put it here. The cosine function starts at 1, cosine of 0 is 1, and the cosine of pi over 2 is 0. So the cosine function looks kind of like this. Yeah, close enough. And we want to find the surface area of this when we rotate it about the x-axis. So in this case, we have our y is cosine x. So we're going to select, because we're going about the x-axis, oh, I didn't put them here. We are going to select about the x-axis, so 2 pi y ds, and then we are going to select this one, dy dx. All right. So we need to know what y prime is, so the derivative of cosine is going to be negative sine. Our limits of integration are going to go from 0 to pi over 2. And we have 2 pi, which I'm just going to put out in front. So 2 pi y times ds is going to be 2 pi times the integral from 0 to 2 pi. Our y is cosine x. So cosine x times the square root of 1 plus negative sine x squared dx. So we simplify up a bit. Negative sine times negative sine is positive sine squared, so times the square root of 1 plus sine squared x dx. So now we need to do this integral. So that's the setup part. How are we going to evaluate this integral? So what should we do first? U sub, good choice. So let's pick u equal to sine x, then du is equal to cosine x dx, or dx is equal to du over cosine x. And then we're going to need to change our limits of integration. So u of 0 is going to be sine of 0, which is 0. And then u of pi over 2 is equal to the sine of pi over 2. And the sine of pi over 2 is 1. So we get our new integral. The 2 pi stays the same. Our lower limit of integration is still 0, but our new upper limit of integration is 1, right? And we have cosine x times the square root of 1 plus u squared, and then we get du over cosine x. And our cosines reduce out, and we're left with 2 pi times the integral from 0 to 1 of the square root of 1 plus u squared du. Okay. Well, that looks a little better than what we had, but we still don't have an antiderivative. So what would we need to do next? Well, we've got a square root, and what do we have underneath it? 1 plus u squared. So this looks an awful lot like what? Trig substitution. So which trig substitution goes with a constant squared plus x squared? Yeah, so this is our tangent. So we let u equal to the tangent of theta. Then du is equal to secant squared of theta, d theta. And once again, we have to change our limits of integration. So 1 is equal to the tangent of theta tells us that theta is equal to the inverse tangent of 1, and the inverse tangent of 1 is pi over 4. Our lower limit of integration says 0 is equal to tangent theta. So theta is equal to the inverse tangent of 0, And the inverse tangent of 0 is 0. So now we have 2 pi times the integral. Our lower limit of integration is still 0, but our upper limit of integration is now 1. So this guy gives us this, and this guy gives us this, because we made another substitution. And then we have the square root of 1 plus u squared is tangent squared theta times du, which is secant squared theta d theta. So then this gives us 2 pi times the integral of pi over 4. 1 plus tangent squared is secant squared theta. So the square root of secant squared is secant theta times secant squared theta d theta, which is 2 pi times the integral of secant cubed theta d theta from 0 to pi over 4. So we're looking at this, and you may remember this guy from last time. So let's go back in time to yesterday. So we did all of this stuff, and in fact we did this exact integral. The integral from 0 to pi over 4 of secant cubed was, remember that big thing we did integration by parts? Some trig identities, had to solve for the integral, put it back on the other side. And after all of that fun stuff, which we're not going to duplicate again, just to let you know. So we'll go back to this step. We started here with our integral. The integral from 0 to pi over 4 of secant cubed theta d theta was equal to this, right? So we're just going to go ahead and take that as our solution and take note to ourselves that if we want the details, that we can find them in 8.1. So see details. We get this for the value of the integral, but then what else do we need? Yeah. So this is the value of this. We need to bring our 2 pi down in front. So we bring our 2 pi down and multiply. So our 2's reduce out, and we get pi times that. So our final answer is pi times the square root of 2 plus the natural logarithm of square root of 2 plus 1. And that would be the surface area of that function. So once again, as we talked about in 8.1, because of that radical, the 1 plus the derivative squared all underneath the radical, oftentimes we end up having to do trig substitutions. These integrals are just plain ugly. Oftentimes we will approximate them, right? So be prepared in the homework for some more Simpson's rule or something else to approximate these values, right? All right, so to find the surface area of this, we're going to need to know y prime. So our value of y prime is going to be 3x squared. We're going to have our integral goes from 0 to 2. And I'm just going to put the 2 pi out in front. So 2 pi y is x cubed, times 1 plus our derivative squared, so 3x squared dx. simplifying this up a bit, we still have the integral from 0 to 2 of x cubed times 1 plus 3x squared. Well, I think it's Zoom that's not working because it's on my screen. It's just not up there. So let's hold on a second. Let me toggle Zoom. Let me end my share. There we go. So apparently Zoom got tired for a second. Give you guys a second to get caught up. So we had 1 plus y prime squared. So that gives us 2 pi times the integral from 0 to 2 of x cubed. 3x squared squared is 9x to the 4th dx. So we look at this, and we need to figure out this integral. So luckily this time, something very nice happens. So if we make the u substitution, u equals 1 plus 9x to the 4th, then du is 36x cubed dx. So we divide by 36x cubed and divide by 36x cubed. This gives us that dx is equal to du over 36x cubed. So then we need to change our limits of integration. So u of 0 is going to be 1 plus 9 times 0 to the 4th. Well, 0 times anything is 0, so we get 1. And u of 2 is going to be 1 plus 9 times 2 to the 4th power. Well, 2 to the 4th power is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. 16 times 9 is 144, plus 1 is 145. And as always, you don't have to do that arithmetic in your head, right? You can just type it into your calculator. I mean, there's no reason, right? So 1 plus 9 times 2 to the 4th power gives us, indeed, 145, right? So now, finally, we have our 2 pi times the integral. Our new limits of integration are from 1 to 145 of x cubed times the square root of u times our dx is du over 36x cubed. So then, as should happen, since we made the right substitutions, our x cubes reduce out, and we can pull the 36 out in front. So we get 2 pi over 36 times the integral from 1 to 145 of the square root of u, and I'll write that as u to the 1/2. So the 2 and the 36 will also reduce, right? So 2 pi divided by 36 reduces to pi over 18. Then the antiderivative of u to the 1/2 is we add 1 to the exponent and divide by it. So we get u to the 3/2 divided by 3/2. And we need to evaluate that from 1 to 145. So before I start evaluating, I'm going to simplify. We can always think of u as a fraction over 1. So if you have a fraction divided by a fraction, dividing by 3/2 is the same as multiplying by what? Well, what's the reciprocal of 3/2? 2/3, right? So this is pi over 18 times 2/3 times u to the 3 over 2. Once again, we get a few things that reduce out. And I'm going to simplify first before I do my f of b minus f of a. So the 2 goes into 18, leaving 9 behind, and we end up with pi over 27 u to the 3/2. And that's evaluated from 1 to 145. So now we do pi over 27, and if we plug in 145, we get 145 to the 3 halves minus 145 to the 3 halves minus 1 to the 3 halves. So then that gives us pi over 27, and the 3 halves is going to be the square root of 145 cubed, or 145 times the square root of 145 minus 1 raised to any power is 1. So note, the 145 to the 3 halves is the same as the square root of 145 cubed, which, when we break it down, right, that's 145 squared times 145, and the square root and the square undo each other, so 145 times the square root of 145. And that would be our exact answer for the surface area of y equals x cubed rotated about the x-axis between 0 and 2. All right. The next thing we want to talk about is something that may at first seem a bit paradoxical. So let's consider the following curve, f of x equals 1 over x, defined on the interval from 1 to positive infinity. Well, let's find the volume of the surface when we rotate it about the x-axis. So just to remind us, let's make a sketch of what this looks like. So the curve 1 over x, if that's 1 and this is 1, looks like this, the reciprocal function, and then as x gets really, really large, 1 over x gets closer and closer to 0, right? So we want to cut this thing off and rotate it about the x-axis, right? That's terrible. That's better. So we get something that looks like this. So it looks kind of like a trumpet or something, right? Or like a long horn of some sort. And we want to find its volume. So the volume, when we did that, we used the disk method, right? So the volume of each disk is going to be pi r squared times dx. So we're going to have the integral from 1 to infinity of pi times our radius, which is going to be 1 over x squared times its thickness, dx. So cleaning this up a little bit, we get the integral from 1 to infinity, and pull our pi out in front, 1 over x squared dx. So that's the integral from 1 to infinity, bringing it up to the top, x to the negative 2 dx. So our antiderivative is going to be x to the negative 1 divided by negative 1, and we're going to evaluate that from 1 to infinity. But before we evaluate, let's clean it up a little bit. So it's negative pi over x evaluated from 1 to infinity. So we just use the negative exponent to put the x back in the denominator. Dividing by a negative just made the whole thing negative. So now, a constant divided by infinity is going to be equal to what? 0. Minus a minus makes it plus. And we put in 1, we're going to get pi over 1. So the minus minus becomes a plus. So 0 plus pi over 1 is going to be pi. So the volume of the solid is pi. Okay. So the volume of 1 over x on the interval 1 to positive infinity is pi. So that integral converges, so we say that the volume is pi cubic units. So let's go to the next part. Let's find the surface area of the same function. So our surface area is the integral from 1 to infinity of y times the square root of 1 plus y prime squared dx. So let's calculate our pieces. So y is 1 over x, which is x to the negative 1. So our derivative is still negative 1 over, skipping a step there, is still negative x to the negative 2, which is negative 1 over x squared, right? So now we plug into our formula. So we have the integral from 1 to infinity of y, which is 1 over x, times the square root of 1 plus negative 1 over x squared dx. Sorry, there's a 2 pi in that formula, right? I left off the constant. It's not going to matter in the end, but there is a 2 pi, right? Because it was 2 pi y ds. Okay, so we have then, cleaning this up a little bit, the integral from 1 to infinity of 1 over x times the square root of 1 plus negative 1 over x squared. A negative times a negative is positive. X squared times x squared is x to the 4th dx. So now we've got to try to integrate this thing, and it turns out that is nearly impossible, or it is impossible, but at least with an antiderivative. But it turns out we don't need to. We need to make a few observations. So observation 1, for x greater than or equal to 1, the square root of 1 plus 1 over x to the 4th is greater than or equal to 1. Why is that true?
Because under the square can never be negative.
That is true. But if you take the number 1 and you add some tiny number to it, no matter how small it is, 1 over 1 plus x to the 4th, this is always positive. Right? So that's strictly greater than 0. So if you add something bigger than 0 to 1 and then take its square root, are you ever going to get 1? No, right? So in fact, we can get rid of this. This will always be bigger than 1. Because if you take the square root of a number bigger than 1, it will get smaller, but it will never be 1 itself. The only way to get 1 as a square root is to take the square root of 1. So this will always be bigger than 1. So if we want to be a little more explicit, this is bigger than this, which is equal to this, which is this, right? Well, then that tells us that the integral then on 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4th dx, by the comparison theorem for integrals, this integral has to be bigger than the integral from 1 to infinity of 1 over x times, and I'm going to put it in 1, right? Maybe I should use a different color than red. Make you blue. Because we're replacing this thing with this, right? So if we replace a function with something that is always smaller than it, then the integral must therefore be smaller, right? So this integral is bigger than this integral. Well, we can calculate this integral because we know how to integrate 1 over x. This is equal to the natural logarithm of x evaluated from 1 to infinity. But this integral, this diverges to positive infinity. Therefore, the integral from 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4th dx also has to be positive infinity. So since we've shown that that integral is bigger than a known integral that goes to positive infinity, so if you're bigger than infinity, you have to be infinity, right? So then what does that tell us about the surface area? So the surface area of f of x equals 1 over x when rotated about the x-axis is infinite. Well, that's a bit of a problem. Let's go back to our picture here. So we've got our little horn-looking thing. So its volume is pi, and what's its surface area? Infinite. So what does that mean in terms of our paradox? Well, if I had pi cubic units of paint, what could I do? I could fill up that horn with paint, right? But then what would happen if I tried to paint the surface of this? How much paint would I need? An infinite amount of paint. Right? That seems a bit paradoxical because it has a finite volume but an infinite surface area. So what's going on here, right? So something doesn't pass the smell test here, right? So you've heard me allude to this fact before that mathematicians like to hide our dirty laundry at infinity. It's a great hiding place for a lot of stuff. Infinity can eat a lot of different things. So I'll let you guys think about this for a while. Don't, kind of like when we did the integration by parts one, the paradox 1 equals 0. Don't lose any sleep over this, but don't overthink it either because the explanation is, once again, not nearly as deep as you might think. It's more surface than it first appears. So don't beat yourself up over this, but I am going to leave you with a cliffhanger on this. I want you to think about it a little bit. So why can we get a finite volume but an infinite surface area for something? All right. So